As we continue our discussion of fire hydrants, we're going to examine some of the specific components of different types of fire hydrants. We'll start with the inlet pipe, and is probably intuitively obvious. The inlet pipe is simply the pipeline from the water distribution main to the fire hydrant. We'll use this standard drawing that is actually one of the standard drawings El Toro Water District uses for new construction to kind of illustrate some of these components as well. So as we said, the inlet pipe is simply the pipeline from the main line coming up to the fire hydrant assembly itself. We've talked before about the term auxiliary valve. It's simply the valve on the hydrant run, or what some people will call a hydrant valve. So it's there to provide isolation for the hydrant for maintenance, for repair, for replacement, whatever kind of work is going to require a shutdown of the inlet pipe. That hydrant valve is there to provide. As we talked about, this kind of standard drawing will show that piece of the overall assembly as well. One of the interesting things about the auxiliary valve and its location, in the book it's going to say that the auxiliary valve should be connected directly to the hydrant, meaning the valve would be connected over on the far right hand side of this drawing, as opposed to where it's shown in this exhibit and where it was shown in the picture here, both of which show the valve closer to the main line, or even in some cases, as shown in this exhibit, connected to the T on the main. The reason why the book suggests that the valve should be over at the hydrant is because that might help to locate the valve. You know where the hydrant is, okay, now you know where the valve is. And I understand that concept, but there are some very practical reasons why I would never put the valve there, and most agencies probably wouldn't. And the primary reason for that is fire hydrants have a nasty habit of jumping in front of moving vehicles. And when that happens and you get a little fountain like this, then it needs to be isolated. It needs to be shut off. And if that fire hydrant valve, if that auxiliary valve is connected directly to the fire hydrant assembly, that means that valve for sure is going to be directly underneath that fountain of water. This particular picture was taken just a week or so ago in the El Toro Water District service area, and you can see a couple firemen who are standing under that geyser trying to shut off a valve that was not connected directly to the hydrant, but was close enough that it was still in that in that condition. And for those that have ever had to do it, that water's cold. What comes up must come down, and comes down at some velocity. So not only is it wet, but it can be a bit painful when that water's coming back down and hitting you. So it turns out these two firemen, our staff is typically the ones we would want to shut the valve off, but the fire captain said, nope, those guys are training, let them do it. So they got to go into the fun of that particular condition. The difficulty though is if you don't know what you're doing, and in this case they shut that valve off, but they shut it off way too fast. It didn't blow anything up, but we definitely saw a surge in our system that pressure sensors picked up. So one of the other reasons I'm never a big fan of having the fire department shut those things off, but I'm never going to be able to get them to stop doing that. So in addition to the concern about being able to access that valve in the case where the hydrant's been knocked off, if the valve is, depending on where the hydrant is, if it's behind a sidewalk, for example, and if you go back to this picture, if it's set right behind the curb, that's one thing. If it's set further back, like in a residential neighborhood, maybe it's in the lawn, if you put the valve right at the hydrant, then that valve is also either going to be on that property or perhaps even in the sidewalk, which is also a dangerous condition. So a lot of reasons why we're typically going to have the valve separated out, connected typically to the T. And once again, if I've got some problem with that inlet pipe, then having the valve out of the T allows me to isolate that entire line. The next piece we'll talk about is a hydrant bury. And the term bury is simply the term for the fitting that connects the inlet pipe to the body of the hydrant itself. The point being, and you can see in this case, it's a kind of fabricated 90, so you don't have a separate 90-degree bend. And if you think about the forces and velocities that are gonna occur when you have a significant fire flow, and velocities that instead of 5 feet per second, maybe you're 25 feet per second, and you're moving perhaps 2, 3, 4,000 gallons a minute, that can create a lot of stress on the assembly. So having this fabricated fitting will help to hopefully keep things together, as opposed to the potential issues you might have if you had a separate 90-degree bend down there. So once again, looking at that standard drawing, there's your hydrant bury, which simply connects your inlet pipe to the fire hydrant assembly itself. The concept of a breakaway spool, once again, as we've talked about, hydrants that get knocked off. If you have a rigid connection that when that hydrant gets hit is going to do damage to the bury below ground, then it's a much more difficult repair. So the breakaway spool is this spool above ground, and you can see the little line in the spool, which is a manufactured defect in the spool. So if this hydrant gets hit, it should snap that spool where that little defect is created. And the goal there being that if that's what breaks, then we can unbolt the spool, put back a new spool, maybe even replace the same hydrant without having to dig out the sidewalk, without having to dig out and replace the entire bury. So it's a great idea to help minimize the magnitude of a repair in the event that the hydrant is hit. In addition to the breakaway spool, oftentimes the bolts themselves that connect the flange are what's called breakaway bolts. They're also manufactured a bit differently, so they should shear if the hydrant is hit and hopefully minimize any damage to the facilities that are below ground. The main valve is also sometimes known as a hydrant valve, not to be confused with the auxiliary valve, but it is a valve within the body of a dry barrel fire hydrant. So in a wet barrel fire hydrant, you do not have a main valve. In a dry barrel fire hydrant, the main valve is really the valve that opens and closes the entire fire hydrant. So looking at different types of main valves, and again, only in dry barrel fire hydrants, the first is a compression valve, and in all cases the valves can be at the bottom of the assembly. In this case, you can see the compression valve down at the bottom, at the very bottom of the barrel. The whole point being that, and we'll talk in the conversation about wet barrel and dry barrel, we're keeping water out of the barrel of the hydrant. So the compression valve simply allows water pressure in the pipe because the valve closes as it's lifted up, so that water pressure is helping to seat the valve and helping to keep it closed. When you turn the operating stem, it pushes the valve plate down, which causes the hydrant to open. Another view, and this is actually a cutaway model of a fire hydrant that I saw at a convention. So same thing, you can see the operating assembly, and then you can see the valve itself down in the bottom, a compression valve that's going to seat against the base of the hydrant, and again, water pressure itself would help to keep it closed. A second type is simply a slide gate, which is very similar to a gate valve. So you have a valve gate that's going to move up and down with the operation of the stem. It simply raises and lowers the slide gate, much like a gate valve does, to open and close the hydrant. So again, down at the bottom of the assembly, but rather than a compression valve, it's a gate valve. The third type is called a toggle valve or a Corey valve. They mean the same thing. So you see on the exhibit here where it says Corey, the outlet of inlet of the hydrant is coming from this direction, and the valve would seat right in the pipe there. So it opens and closes horizontally through a kind of toggle assembly. Another picture of it here. This one is reversed, so the valve is actually, this one shows the valve in a closed position. So the two arms move up and down to pull back or push forward the valve assembly to open and close the fire hydrant. So those are the three types And there's another exhibit showing a closed Corey valve. So the three types of main valves, and once again the term main valve implies a dry barrel fire hydrant. The three types of valves are the compression valve, the slide gate, and the toggle or Corey. And again, toggle and Corey mean the same thing. So make sure you're familiar with what the three different types of main valves are for dry barrel fire hydrants. The barrel of the fire hydrant itself, we're talking about the material of the fire hydrant. This is the body of the fire hydrant itself and the above ground portion. Originally these were made out of cast iron. At some point then they became the material of the day, so to speak, was bronze. You're now seeing a lot of ductile iron for fire hydrants. In fact, at El Toro Water District, all of the fire hydrants that we install today are ductile iron fire hydrants. And the real reason is cost. The difference between a bronze fire hydrant and a ductile iron fire hydrant is $700 to $900. On a typical residential fire hydrant, the ductile iron fire hydrant costs around $1,150, where a bronze hydrant is over $1,800. On the commercial hydrants, it's almost $1,600 for ductile iron, $2,400 for bronze. So there's a significant cost difference between the ductile iron and the bronze material. We've been installing a lot of ductile iron fire hydrants to great success. We've not seen any problems with them. So without any driving reason to spend the additional money, it doesn't make any sense. So we've pretty much converted to the ductile iron. The head of the fire hydrant we can also refer to as the nozzle section. On a dry barrel fire hydrant, that head is going to include the operating nut, which really distinguishes the hydrant. So that kind of five-sided operating nut you see on the top, which again is designed to accommodate a special hydrant wrench that you've got to have one of those really to operate this fire hydrant. There's ways to jury rig it, to be sure, but the goal is to make unauthorized use of the fire hydrant as difficult as possible, and only those that have the wrench should, at least with some level of ease, be able to operate the fire hydrant. But again, where there's a will, there's a way. The nozzle of the fire hydrant is simply the outlet. It's the discharge portion of the fire hydrant itself. There are a couple different types. Two nozzle design, meaning a fire hydrant that has two outlets. Typically speaking, we refer to that as a two-way hydrant. The first outlet is a 2.5 connection, which is typically going to be for a fire hose. The second is a 4-inch connection, which is typically going to be for usually the connection between the fire hydrant and the fire department's pumper truck, where they may be boosting pressure. Keep in mind that when you have a fire flow condition, the pressure in the distribution system and the pressure feeding the hydrant by design may be as low as 20 psi. So the fire department trucks are designed to take water from the hydrant and pump it up to higher pressure. So depending on what's going on, you may have a hose connected directly to the 2.5 inch, or they may be taking water from the 4 inch and boosting pressure through the fire truck itself. Usually the two-way hydrants are you're going to find those in residential areas, which are going to have somewhat less intense use, somewhat less flow as well. The second type is the 3-nozzle design, and as you can see in this exhibit, you've got instead of the 2 nozzles we previously had on the two-way, a 4-inch and a 2.5 inch. In the 3-nozzle design, we're basically adding another of the nozzles. Oftentimes a 2.5 inch, and that's what you can kind of see on the upper one, and the lower one actually shows it appears that there's 2 4 inches, so they can be either way, but the 3-way usually is going to be another 2.5 inch, but again, that's not written in stone. The 3-nozzle design is what you're typically going to see in commercial areas where you may have higher demands, where you may have more potential intense fire conditions, or what the fire department is trying to make sure they're prepared for. In all cases, these nozzles should have caps on them. That's going to be part of the maintenance responsibility for the agency to make sure those caps are in place. So to kind of summarize, looking at this standard drawing again, remember the inlet pipe goes from the main line to the berry. The valve that provides isolation of the assembly and the inlet pipe itself is the auxiliary valve. That fitting that connects our inlet pipe to the hydrant assembly is the hydrant bury. We talked before about valve cans, which provide access to the valve from the street surface, usually with some sort of metal lid that's rated for traffic. And then the connection from the valve can to the valve itself is some sort of piping material, a valve stack. And like I said, when we talked about valves, that's really just PVC pipe in the El Toro Water District and many other agencies as well. You're just trying to provide an open space that keeps the operating nut of the valve clear. And then, of course, the outlet of the fire hydrant are the nozzles. So those are the components that we want to make sure we're clear on for fire hydrants. And as we continue our discussion, we'll take a look at some of the specifics of hydrant operations, uses, and maintenance in the next section.